It's Manisha Lewis Cole again, and today I want to talk to you about Pascal's triangle. Blaise Pascal, French philosopher, mathematician, scientist, and inventor, is who the triangle was named for. This is Mr. Pascal. He actually was not the originator of the Pascal's triangle. This triangle has gone back to ancient times as far as the Persians and the Chinese in the 11th century. But he perfected the Pascal's triangle, the binomial theorems, the formulas that are associated with it, hence his recognition for the triangle. Well, today I want to take you down a little bit of what this triangle is. So let's look at how to create Pascal's triangle. The first thing we do is we notice that the diagonals of, first of all, the triangle is an equilateral triangle and it goes on and on and on. And we begin with ones along the diagonals. So you will begin with 1, 1 and 1, and then we get to the third row. The uniqueness of creating this triangle is each of the two numbers above are combined. So you will see I have 1 plus 1 that gives us 2. To create the next row, we would then combine 1 and 2 to get 3, 2 and 1 to get 3. And as I just stated before, we go along the diagonals with always having a 1. And then you would just continue. 1 plus 3. Again, 1's on the outside. 1 plus 4. 4 plus 6. 6 plus 4. 4 plus 1. And then again, 1's on the outside. So Pascal's triangle, if you notice, creates kind of a pattern. And that pattern turns out to be something rather fun if you look at it. Like we just stated, all of the diagonals are ones on either side. Then when you start to go internally, what do you notice? 1, 2, 3, 4, 5. Those are your counting numbers. Your counting numbers are in the second row, either diagonal. Then if you notice the third row, we get numbers like 1, 3, 6, and 10. Those are going to be considered your triangular numbers. And the reason why we call them triangular numbers is if you look at a triangle, I'm going to move this over for a second. I'll just move it down. Triangular numbers are the numbers that create a triangle when listed. So we have 1, 2, 3. That is a triangular number because it creates a triangle. The next one would be 6. 1, 2, 3, 4, 5, 6. Creates another triangle. And the next one in the row is 10. Think of your bowling pins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Horrible triangle, but it's still a triangular number. So those are some of the fun facts that you will find that comes along with Pascal's triangle. So 2 things that we've learned thus far. When you add the rows below, the row above, you get the number below. There's always going to be a 1 along the diagonal. The second row is your counting numbers, and your third row is your triangular numbers. So those are some fun and interesting little facts, and there are some more things that go along with those fun facts, like you can find that there are multiples of the powers of 11. 11 to the first power is 11. 11 to the second power is 121. 11 to the third power is 1,331. There are quite a few facts and quite a few interesting things when you deal with Pascal. But some of the things that we want to talk about today in our mathematical concept of Pascal deals with what exactly is this triangle used for mathematically. Pascal brought us around 1623 when he was born. He started, I want to read something. It was stated that through a challenge, and I don't want to get it wrong, he was asked a question by an amateur mathematician and noted gambler. So it's funny that math came out of gambling. That suppose you're given 24 rolls of a pair of dice, what is the probability of throwing double sixes at least one time? This brought us to his love, which was probability. And Pascal began the theory of probability. And the theory of probability further went along and eventually became this triangle. So before he started the actual probability, he had to find out combination. And the combination that we are familiar with N choose R. N choose R is basically N factorial. And factorial is basically multiplying all of the numbers from that number down to 1 times R factorial. Again, the numbers from R down to 1 and minus R factorial. So how does this relate to Pascal's triangles? Let me show you how. Let's say, for instance, we wanted to use 4 choose 3. 4 choose 3, basically the N and the K, would equal 4 factorial, 3 factorial, 4 minus 3 factorial. So again, I stated factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1, all multiplied by 4 minus 3 factorial, which is just 1. So what do we see here? We can cross these out and we're just left with 4. So that tells us there are 4 combinations. So how does this relate to Pascal's triangle, you ask? Glad you asked that question. It relates because this 4 choose 3 means to go to the 4th row. We always start with 0. 1, 2, 3, 4. This is your 4th row. And then we go in 3 terms. Again, this term is always 0. So 0, 1, 2, 3. And what do we notice? This 4 is the same as this 4. So that's basically how you read Pascal's triangle along with your combinations. So 4 choose 3. We can use Pascal's triangle by basically going again. Remember, this is row 0, 1, 2, 3, row 4. Term 0, 1, 2, 3 correlates. The next thing that we can talk about are your binomial expressions. The binomial expressions are basically when you're adding 2 variables, binomial meaning 2, and raising it to some power. Let's just choose 7. And the reason why I want to choose 7 is because I don't have it up here, and we're going to check it both ways. You have to do the 8th row. So right now we only have 5 rows. So 6 would be 6. And the 7th row would be 1, 7, 21, 35, 35, 21, 7, and 1. So this right here is going to be very, very specific when we need to do the binomial expressions. So now just think, if your teacher asks you to take x plus y to the 7th power, traditionally we would write x plus y 7 times, which is what it means, and then we would have to multiply. And like the squared and the 3rd power is pretty easy, but when you start getting to the 7th power, it gets a little complex. So this is so neat that these numbers, 1, 7, 21, 35, 5, 21, 7, and 1. I'm going to have to rewrite that because I don't have enough room. Actually corresponds to the coefficients of each of these terms. Not only do they go along with the coefficients, you then now look at your x and y terms. And you would have 1 for each coefficient. So therefore there are 7 terms for the 7th row. And the unique part, how we're going to combine these two, we basically start with x equal to your 7th term, y equals to 0. And then you just go down, x6, x5, 4, 3, 2, 1, x to the 0. And then you go up with your y's, y1, 2, 3, 4, 5, 6, 7. And then to finalize and write this binomial expression out, you would basically just combine. We really don't use the coefficient 1, so we could just say x to the 7th and y to the 0 is just 1, plus 7x to the 6th, y to the 1, 21x to the 5th, y squared, plus 35x to the 4th, y to the 3rd, I'm going to come here, plus 35x to the 3rd, y to the 4th, 21 x squared, y 5th, 7 x, y to the 6th, and lastly, plus y to the 7th. So basically, again, combinations and binomial expressions have been part of using your Pascal's triangle to make number theory a lot simpler and easier to use. Some other quick facts that I want to share with you are the binomial theorem. The binomial theorem states basically, you use this when you don't have that simple binomial where you can just do like I just did and use a line. Sometimes we, and often, do not have just something simple. You might have something like 2x plus 1 to the 4th power. We cannot just simply use the binomial theorem we will use the binomial theorem. We cannot just simply use binomial expressions and Pascal's. You have to actually combine the combinations and the binomial theorem to get this completed. So first, what we would have to know is the binomial theorem. And it states x plus y to the n power is basically, this is when we have to come with sums. So we use this sigma of n to the k equals 0 Here we go with our combinations. N choose K. N choose K. X to the N minus K. Y to your K. How do we solve this? We just plug in. Your X term is going to just be 2X. So therefore, we will substitute. N is 4. K is 0. Then we're going to multiply by 2x to the n, which is 4 minus 0, times y, which was just 1, to the k, which is 0. And then now we go to row 4, choose 0, and remember that first term is just 0. So we get 1 times 4 minus 0, so 2 to the 4th is 2 times 2 times 2 times 2, which is just 16. X to the 4th times 1 is just, 1 to the 0 is just 1. And remember, it's a sum. So now we do 4, choose 1, 2x, 4 minus 1, 1 to the 1. 4, choose 1. We will go to row 4. Remember that's 0 and that's 1. 2 to the 3rd is 8x to the 3rd times just your 1. Now we add, and I'm just going to bring that down here. 4, choose 2. I'm sorry, I did not mean to put that half there. 4, choose 2. Remember 0, 1, 2, which is 6 times 2x to the 4 minus 2 times 1 squared, which will give us 2 to the 2 is 4x squared. And we have to multiply that by 6 and 1. 6 times 4. X squared plus, now we have to do 4, choose 3, again 4, 0, 1, 2, 3, and we come back. Remember, we did this in our original problem. 4 times 2x to the 4 minus 3, 1 to the 3, and we get plus 4 times 2 to the 1 is just 2x times 1. And then last but not least, we have 4, choose 4, which is again 0, 1, 2, 3, 4, which brings us back to 1. And so plus 1 to the 2x, I'm sorry, I don't have much. 4 minus 4 is just times 1. 1 to the 3rd is just times 1. So let's write this final answer. And let's combine all of these. Hope I didn't go too fast. You were able to follow along. 2x plus 1 raised to the 4th power is, I'm sorry, start here. 16x to the 4th plus, oh, we didn't multiply that. That's 32 x to the 3rd plus 24x squared plus, we didn't multiply that. That would just be 8x plus 1. Look how quick and simple that was compared to the mathematics that we've had to do in the past. I hope you've enjoyed my little presentation on Pascal's triangle, its uses with simple patterns. There are many more to discover. The Fibonacci series, we talked about the 11th power. There's also special patterns and all kinds of things, but mathematically, this is what it's used for, and I hope you've enjoyed my presentation. Thank you and have a good day.